So tonight, we have a very cool event. Tonight, I'd like to introduce Dr. David Grinspoon. Dr. Grinspoon is an astrobiologist, award-winning science communicator, prize-winning author. He's a senior scientist of the Planetary Science Institute and is involved with several interplanetary spacecraft missions for NASA, the European Space Agency, and the Japanese Space Agency. Dr. Grinspoon is also a host of the popular podcast Star Talk All-Stars. And many of you may know Dr. Grinspoon from his former role as curator of astrobiology at the Denver Museum of Nature and Science. Dr. Grinspoon, thank you so much for joining us tonight.
Oh, thanks very much for having me. It's such a pleasure to even virtually be back here at the planetarium at DMNS to talk about one of my favorite topics. We are poised for a new decade of Venus exploration. Those of you that have been perhaps seeing me speak for a few years occasionally know that my big obsession, or one of my big obsessions, is the planet Venus. And you may have heard me for, well, I was going to say years, but honestly, for decades, you may have heard me sort of wishfully talking about why we need more Venus missions. And I've been part of this community that's been proposing missions over and over again, and then always losing out to other plans to go other places. So it's pretty exciting now to be able to talk to you about Venus from the standpoint of being part of a team that now has an approved mission that is going to launch later this decade. So I'll get back to that. Let me back up and start with some background here. I'm going to share my screen. See if I can make this work. Let's see, PowerPoint, share. Full screen. Boom. And Mitch, you'll tell me if I'm showing presenter mode instead of actual.
And you are showing presenter mode.
Okay.
At the moment.
Somehow it comes up 50-50. So now I'm going to swap display. Okay. Now are you seeing my presentation?
Yes. There we go.
Excellent. Thank you for that. Okay. So yeah, I want to talk to you a little bit about the past exploration of Venus to sort of set up what's happening now, and then end by telling you about the decade of Venus that's to come. I've always been fascinated by what we now call comparative planetology. Let's see, can I get this to advance? Come on. Why it won't advance? What if I just cheat and do this? Now is it gonna? Oh, good. Okay. I've always been fascinated by comparative planetology, the fact that we live in this new age. It's still new, where we can look at the planets close up with spacecraft and come to understand them as not just as dots in the sky, but as worlds that we can compare and contrast and understand their similarities and differences, and come to a deeper understanding of how planets work, including how our own Earth works. And amongst all that comparing, I've been especially interested in and fascinated by this trio of worlds, Venus, Earth, and Mars. Venus and Mars, of course, being the two nearby most Earth-like planets, being rocky worlds with substantial atmospheres. They just make for really interesting comparisons. The evolutionary divergence of these three, born at the same time, born nearby in the solar system, and they've all ended up in such different states with such different climates and environments and surfaces, geology, atmospheres. And understanding that comparative evolution has really been most of what my research career has been about. And one interesting byproduct of that is that we do gain a lot of insights into planets like Earth in terms of the question of habitability, what allows a planet to have life, and also important questions of climate, which of course now are important not just because we're interested in the science of how planets work, but because we have a serious societal issue with climate change. And one source of insight into that is comparative climatology of the planets. And the Venus-Earth comparison is very interesting in that light. And we gain a lot of perspective on Earth's climate by looking at an extreme greenhouse climate like Venus. And we even learn some practical things from doing a better job modeling Venus, which feed back and help us do a better job modeling climate change on Earth. So that's one of many reasons why I'm so fascinated by this comparison. And then of course, I wonder why instead of, well, I can just advance it like this. When I try to use the arrow key, it just goes boop, nothing happens. But when I double click on the screen, it worked. Anyways, I have a workaround. So the history of ideas about Venus, of course, is rich, and I won't go into much here except to remind you of what a beautiful sight Venus is in the sky. Right now, it's a morning star. It bounces back and forth between evening and morning as it passes Earth on its inside orbit. And oftentimes you see it up near a crescent moon, as in this image shot a few years ago outside of Boulder, Colorado. And so the fact that it's a lovely and bright object, the brightest object in the sky, except for the full moon in the night sky, has drawn human attention for a long time. And it was an object of worship and wonder and prediction for a long time. And then, of course, fast forward to the scientific age, but the pre-spacecraft age, we knew some things about Venus. Early astronomers correctly deduced that it was about the same size as Earth, and correctly deduced that the great brightness of Venus in the sky is because it's completely covered with reflective clouds. But before we had spacecraft, we didn't know anything about what was beneath those clouds. And there was this sort of common idea of Venus as maybe a sort of tropical planet. The idea being, well, it's a little bit closer to the sun, but it's similar to Earth in size, and it's covered with clouds, and clouds mean water and rainfall. And so maybe it's kind of a jungle world. And that was a very common idea of Venus in science as well as science fiction, right up to the space age, and led to all kinds of fun stories like Lucky Star in the Oceans of Venus was a favorite of mine when I was in 5th grade, where Lucky, our hero, Lucky, travels to domed cities on the floor of the deep ocean on Venus and battles telepathic frogs that live on Venus. And basically the forces of good win out over the forces of evil. Fortunately, in that story, unfortunately for stories like that, the oceans of Venus evaporated when we learned more about the planet, but not before. There was also some fun, goofy science fiction like this movie, Queen of Outer Space, starring Zsa Zsa Gabor as the chief Venusian scientist in sometime in the 1950s. I don't remember the exact year. So all this sort of historical Venus as a maybe kind of Earth-like place really went through a radical change when we started going there with spacecraft. And the first was Mariner 2 in 1962. And this is a depiction of Mariner 2, and it was a very simple spacecraft. It was the first ever successful spacecraft to another planet. And it basically had one scientific instrument that it used at Venus called a microwave radiometer, which measured the intensity of radiation across the disk of Venus to try to understand where the anomalous microwave radiation that had been observed from Earth was coming from. Was it coming from the surface or from the upper atmosphere? And Mariner 2 proved that this radiation was coming from the surface, and that meant that Venus was hot, much, much hotter than Earth, far too hot to have liquid water or living organisms. And that was treated as sort of a disappointment. This is the headline in the New York Times after these results were announced. Venus says no. And they said that the message from Venus may mark the beginning of the end of mankind's grand romantic dreams. And right above that, Mars now remains our only hope of turning this universal dream into reality. That is the dream of widespread life in the universe. So it was treated as a big disappointment when Venus was found out not to be Earth-like. And it was only gradually, after many, many more missions and many, many more observations and decades more of modeling, that we started to realize how interesting a place Venus really is and how relevant it is for our trying to understand Earth-like places in the universe. This is still something we're figuring out. But the early missions gave us the sort of basic ability to do comparisons between Venus and Earth. And what you'll notice here is that what's interesting about Venus, and why I think I've always been sort of drawn to studying it, is that there are some ways in which it is such an Earth-like place, like remarkably Earth-like in terms of its diameter. It's very similar. Venus is, whoops, what just happened? PowerPoint crashed. Oh, that's interesting. I'm just gonna reload it and keep talking while it reloads. There are some ways in which Venus is remarkably Earth-like. It's the same size virtually as Earth and the same mass as Earth. Let's see, open recent presentation. This should work. Sorry about that. I don't know why it crashed. Hopefully it won't crash again. There it goes. All right. All right, Mitch, let me know if anything's not right.
Looks good. Looks good.
Okay.
We're back on.
All right, let me just forward to where I was. So yes, to recap, here we are. So remarkably similar in diameter, mass, and therefore escape velocity, which is very important for evolution of atmospheres and so forth. And then remarkably different in terms of current environment, where the surface pressure on Venus is almost 100 times that of Earth. The temperature here in centigrade is much, much higher. So that's, you know, almost 900 degrees Fahrenheit, the surface temperature. And strikingly, the water abundance is 5 orders of magnitude different. So Venus, the Earth has 100,000 times as much water on Venus as Venus, which is amazing given how similar their bulk composition is. And so they seem to be, I mean, the density is very similar. You can tell because they have similar mass and similar size. And so they seem to be made out of the same stuff, more or less. And they were formed at the same time, presumably out of the same raw materials. So somehow it seems as though Venus lost most of its water, 100,000 times the water that it has now, if our understanding of that evolution is correct, unless somehow it formed much drier than Earth, which is possible, but we don't really know why it should. So that seems unlikely. So this is sort of a big puzzle. Why did Venus and Earth end up so different from one another? After Mariner 2, we had a series of missions. Both the Americans and the Soviet Union was very active in the 60s and 70s, and very successful, I might add. The Soviets were never successful at Mars, but for some reason, I have my theories, but nobody really knows, maybe just luck, but that for some reason they were very successful at exploring Venus. In fact, the Soviets are the only ones that have so far landed on Venus and survived to do experiments and take pictures at the surface, like this sequence of, these are pictures from 6 different Soviet the Venera surface landers, and you can see they're all different locations, but they have this sort of similar quality of kind of platy rocks, which we now interpret to be eroded volcanic rocks. They even got some color images. And that kind of ruddy red light comes about more from the atmosphere than from the surface. It's because the atmosphere and the clouds are so thick, picture a sort of permanent sunset color. And that's what you have on Venus. So the red is more a quality of the light filtering through the air and the clouds rather than a property of the surface. But we did learn that Venus is completely covered with clouds all the time. We eventually figured out those are not water clouds. They're concentrated sulfuric acid with some interesting impurities in them, but we're still trying to figure out what those impurities are. We have some ideas. And that the surface conditions are, it took several more missions after Mariner 2 to figure out just how hot and how high pressure an environment is. But eventually we learned that it's, again, almost 900 degrees Fahrenheit everywhere all the time on Venus, day, night. There's no temperature difference because the atmosphere is so thick and because the planet rotates so slowly, 243 Earth days for one Venus day. So it rotates really slowly in that thick atmosphere. Carries heat all around the planet. So equator to pole, day to night, it's all the same temperature everywhere. Except for if you want to cool off on Venus, the only thing you can do is go up one of the very high mountains and get, 10, 20 degrees cooler, but that's it. And I'm not going to mention every mission that's happened because I want to get to what's new and interesting and planned for the future. But one mission that I have to mention was the Pioneer Venus mission in 1978, which was a very successful, very complex American mission to study the atmosphere of Venus. It had what we call a bus spacecraft, and then 4 different probes, 1 large probe and 3 small ones, which went into different places. There was a day probe, a night probe, a north probe. So we sampled different latitudes and different lighting conditions, different day-night conditions. And much of what we know today about the atmosphere of Venus, the deep atmosphere, especially underneath the clouds, still stems from that 1978 Pioneer Venus mission. And interestingly, it was the last time there was an American mission to the atmosphere of Venus. So the last time we had a probe that went down through the atmosphere of Venus was 1978. And we've just gotten the green light from NASA to do it again. And we're going to, with a mission called Da Vinci that I'm involved in and that I'll tell you a little bit more about. And we're going to launch in 2029. So that's quite a gap from 1978, from the last time we had a entry probe into Venus. And the good thing is we've learned a lot since then about Venus and about exploration technology and miniaturization and instrumentation. So there's a lot that we're going to be able to do with this Da Vinci mission that we couldn't do with our 1978 technology and our less sophisticated knowledge of planetary environments. So something to look forward to. But anyways, Pioneer Venus really, combined with the other American and Soviet missions in the 60s, 70s, and early 80s, really gave us the overall picture of the Venus environment. There's a lot of details that we're still working out, but as far as that really hot, really dry environment, what the atmosphere was basically made out of, what the surface was like, at least in a crude sense, we knew by that point. And that gave us a kind of, at least a kind of cartoon version of a cartoon understanding of the evolution of Venus. How did these seemingly identical twins evolve into such different types of planets? And because we're Earth-centric, we'll pose the question, where did Venus go wrong? And a simple answer that's probably correct to some degree is that it was born too close to the sun. Imagine 2 planets more or less formed out of identical stuff, but one is about 30% closer to the sun than the other. That means it gets about twice as much sunlight because of what we call the inverse square law, where if you're twice as far away, you get 1/4 as much sunlight. Well, if you're a third closer to the sun than Earth, you get about twice as much sunlight. So Venus gets quite a bit more illumination and a lot more energy from the sun. And that led, we believe, at a certain point to what we call the runaway greenhouse, which is a powerful feedback where you have, if you have a hotter surface temperature, that causes more water to evaporate. Water vapor itself is a strong greenhouse gas, and that leads to greater what we call infrared opacity, or absorption of heat radiation by the atmosphere. And that greater absorption of heat heats the surface up more, which causes more water to evaporate, which makes the surface even better at stopping infrared, which heats things up more. That's why it's a positive feedback. The different parts of the cycle reinforce each other, and there's sort of no stopping it once that gets going on your planet. And the end result is that the oceans kind of boil off and the hydrogen escapes into space. And you're left after a while with a planet with no more oceans. And we think that's what happened to Venus. And the result again today is that Venus has only about 1/100,000th as much water as Earth. Well, that's our cartoon understanding, but is it right? And there's still a lot of questions. When did this happen? What really triggered it? How did the evolution of the atmosphere relate to the evolution of the geology? There's an awful lot that we don't know. And a big step towards figuring out what makes Venus tick was the next mission I'm going to briefly mention, which was called Magellan. And this was an American mission that launched from the space shuttle in 1989. Here you can see it launching from the bay of the space shuttle with those solar panels still folded up. They're going to unfold, and this is the big engine that launched it towards Venus. And Magellan had one big instrument, which was also its big communication antenna, but it used this to do radar imaging of the surface. It points towards the planet, bounces radio waves off the surface, records the reflection, and does this over and over again as it orbits and strips around Venus, and then puts together a radar map of the surface, and then periodically turns towards Earth with that same antenna to send the data home, and then turns back towards Venus and keeps mapping. It did this for 4 years. Magellan was an incredibly successful mission, and it really laid bare the surface of Venus for us. And here's a global mosaic of Magellan imagery showing you what the surface geology of Venus really looks like. And very simply, a lot of it is dominated by smooth volcanic plains, what we call flood basalts, a very kind of runny geology, runny lava, very smooth. And then there are smaller areas which are rough and elevated. You can see this sort of rough patch all going along the equator. What just happened? There we go. And these are more mountainous regions, and we call them the tessera. And they're the older regions of Venus. And here's what the tessera look like up close. And tessera are very interesting because they do seem to have a long history of tectonic disturbance and maybe volcanic and maybe ancient times, even erosive modification, where we don't know about that. But we believe that the tessera have clues to the early history of Venus because they're the oldest terrain. And this is where we're going to go with the Da Vinci, the mission I'm going to tell you about. We're going to actually descend over one of these areas of tessera, one of these very mountainous regions, and get the first stereo 3D descent photography of Venus as we go down. So that's going to be really exciting. Yeah, another thing Magellan revealed on Venus is just tons of volcanic landforms, all different kinds of volcanoes. These are called pancake domes. They're about 10 miles across each. And as you can see, the name is because they're very sort of dome shaped, and they're made out of some kind of very runny lava that didn't get very smooth. It kind of piled up and solidified. And then there are these other areas where there have been much more effusive volcanic flows, these sort of lobate shapes. These are all flows of volcanism on the surface. A lot of really just kind of strange and cool looking volcanic and tectonic features on the surface of Venus. And there are also a fair number of impact craters, although the craters on Venus are interesting and kind of strange in a lot of ways. One is that there are not that many of them. There are about 900 on the whole planet, and they seem to be superimposed mostly over these smooth volcanic plains, which themselves don't have a lot of craters in them and seem to have covered up any previous craters before the volcanoes flowed, which gives us a sense that the geologic history of Venus has been kind of strange. A lot of the craters also have these beautiful outflows, probably a result of a lot of melting because the surface is already so hot, and then you cause an explosive impact crater, and that leads to a lot of melting of magma. As I mentioned, the distribution of craters is strange. They're not that many, and it's very uniform, which makes us think the surface is all sort of the same age, that uniform density of craters. They're not clustered that much in any one area of the planet. Contrast that to a planet like Mars, where you look at all the craters, and there are many more craters in the southern hemisphere of Mars than the northern hemisphere. And that tells you that the southern hemisphere of Mars is a much older surface. It's much more pockmarked. It's been sitting and getting cratered for much longer. The northern hemisphere of Mars are not all that young, but they're clearly younger than the southern hemisphere. You see an age difference from the crater distribution. Well, you go back to Venus, you go back to Venus and you just don't see that, which suggests to some geologists that the surface is all roughly the same age, although that's a little bit controversial. And we're still trying to figure out the geological history of Venus. But compared to, say, here you have the history of Earth, where it's all very young. You look at Earth here, and this is a sort of chart showing you how many of the rocks are different ages. So on Earth, all the rocks are much less than 1 billion years old, because Earth is constantly reforming itself. And it'd be very hard to find a 3 billion year old rock on Earth, because they've all been destroyed by the constant geological activity and meteorological and biological activity. Contrast that to the Moon or Mars, where almost all of the surface is more than 4 billion years old. And there's be very hard to find a young rock, 1 billion year old rock on Venus, even maybe on Mars. We would modify this a little bit now. There's been some recent activity, but most of the activities in the past. And what's interesting about this, as revealed by Magellan, is that if you look at Venus on here, there are a lot of question marks, because we still don't really know the geological history very well. But it's clear that Venus is in a category more like Earth, where most of the surface is relatively young and recent, and it's been more active. How active? Is it still active? Well, we believe so, but we're really trying to figure that out. One thing we did learn about Venus, and this is some of my research has been in this area, is that the interactions between the surface geology and the atmospheric chemistry and the climate are very complex. And there's some weird, interesting cycles, because there are gases, we think, coming out of the volcanoes, water and sulfur dioxide, which chemically react and make the sulfuric acid clouds, and then react with sunlight and do interesting things and react with the surface minerals. And there's a sulfur cycle on Venus that's feeding the clouds and coming out of the volcanoes and affecting the surface chemistry that is very complex. In some ways, it's like the carbon cycle on Earth, in terms of the complexity of atoms switching forms between the different realms of the planet in this cyclic behavior that we're still trying to figure out. And this is a very nerdy slide that I'm not going to lead you through in any detail, but this is just an example of some of the research that I've done with some of my colleagues, where we really tried to understand these interactions between the surface and the atmosphere and the clouds. And so we put together a model that has modules that make things happen with the clouds, depending on what's happening with the atmosphere. And then the atmosphere can be affected by volcanoes. And then we let radiation travel through the atmosphere, and all the different parts of it sort of affect each other, trying to simulate the complexity of the atmosphere and the surface. And we've learned some very interesting things by modeling things in this way that I'm just going to not really go into detail. I just wanted to give you a hint of some of the research that I've been involved in, but I want to make sure we have a chance to kind of go through this whole history and then tell you briefly about the upcoming missions, and then make sure that there's some time for you to ask questions if you want. So that's why I'm rushing through some of this stuff. So there are 2 more missions that I want to tell you about before I get to the new missions. And these are, one is a European Space Agency mission called Venus Express. There was this big lull in, obviously the Soviet Union fell apart and stopped sending missions to Venus. And then the United States, for various reasons, mostly having to do with politics and funding and other things, hasn't had a Venus mission since Magellan, other than a couple of quick flybys of missions on their way to the outer solar system. So there's been kind of a hiatus, but fortunately that gap was filled by 2 really innovative missions, one from Europe and one from Japan, which we were fortunately able to collaborate on. And this has all become very international, this effort. And Venus Express launched in, what year did Venus Express launch? It's a good thing I wrote it down because I'm trying to remember all the dates. Oh yeah, it launched in 2005 and was a very quick trip on Express to Venus. It got there in 2006. Venus Express was kind of our first almost like weather satellite at another planet. It was mostly about studying the atmosphere from orbit, but it had some very sophisticated instruments and really gave us a new sense of the way Venus changes over time and all these different timescales and how dynamic the atmosphere is. But another thing Venus Express was able to do was to study the surface of Venus a little bit, even though it was an orbiter. And even though you have those thick clouds, it turns out that if you look at just the right infrared wavelength, right around one micron, it turns out in wavelength, you can actually see the surface of Venus. And by mapping the surface radiation from Venus Express, we were able to notice that the chemistry of some of the areas of young seeming volcanoes on the surface seems different from the chemistry of the rest of the surface. And some of my colleagues on this mission deduced from that they're pretty sure they're seeing evidence of active volcanoes. That's why the surface chemistry is different, because there are fresh lava flows. So this is not indisputable proof, but it seems to be circumstantial evidence from this mission, Venus Express. The next mission I need to tell you about is Akatsuki, which was the first Japanese mission to Venus. Akatsuki was also a pretty amazing mission. And its story is crazy. It launched in 2010. It got to Venus in late 2010. And when it was supposed to be entering into Venus orbit, something went horribly wrong. The main engine basically blew up when it was trying to go into orbit, and Akatsuki did not make it into Venus orbit. It went spinning helplessly around the sun. But it turned out it was spinning helplessly around the sun on a trajectory that was going to bring it back to Venus 5 years later. Which led to the questions: one, would it survive the 5 years, especially because it had to make a couple close passages to the sun? And two, would they be able to get it into orbit without a main engine? Remarkably, 5 years later, Venus Express went back to orbit, and the very clever engineers in the Japanese Space Agency figured out that even without a main engine, they could use the maneuvering thrusters that were not designed for this. But if they fired them all in the same direction for 20 minutes, much longer than they were supposed to normally be fired, it would generate enough thrust so they could barely get into orbit. And they couldn't practice this maneuver because they only had enough fuel to try it once. So it was very touch and go and nerve-wracking and dramatic. But the end result is that they were able to get Akatsuki into orbit, and it worked beautifully. They had to change the mission because it was a different kind of orbit than they had planned. And Akatsuki's still there, still doing science. A couple of the instruments have failed, but it's been an incredible mission. I won't tell you everything that we've learned from it, but one really interesting, surprising result is that there's this sort of ridge in the atmosphere, an atmospheric wave structure. You can see in these images, and you can see in this movie, it kind of comes into view, I think, here. Yeah. See that? Whoops. And that turns out also to be correlated with a surface feature, one of the highest topography features on the planet, called Aphrodite Terra. And we believe that the two are related, that this means that there's this giant wave feature that goes 50 kilometers up in the atmosphere of Venus. That's huge. That is being caused by waves interacting with the winds and the surface mountains. So there's this is a more recent discovery, and we're still trying to figure out what it means as far as the overall circulation of the atmosphere. But apparently you're seeing something really high up in the atmosphere that's related to the surface topography of some of these huge mountains. As the I didn't mention this, but there's something called the super rotation of the atmosphere, where it whips around the planet every 4 days. Even though the solid planet is rotating very, very slowly, the atmosphere above it, driven by solar energy, is whipping around really quickly. Okay, so I really want to get to the new missions, but there's one other category of that I want to describe briefly. Speaking of the clouds, and that is, I just need to tell you about a sort of pet idea of mine that I've harbored for a while, that's recently been getting some attention. And that is the idea that in the middle clouds of Venus, there could possibly be a habitat for some kind of life. Now, I've already mentioned the surface conditions are so forbidding and intense, and it's so hot and high pressure. There's no way, certainly life as we know it, depending on water and organic molecules, couldn't survive at all on the surface of Venus. But interestingly, there is a region up in the atmosphere. You'll notice on this graph here that's got temperature with altitude and pressure. There's a region in the middle clouds here where the surface pressure is similar to the surface pressure of Earth, because this is 1 bar. This is Earth surface pressure right here. And this is in Kelvin degrees. So the Earth surface pressure is, Earth surface temperature is right around 300 Kelvin. And you'll notice that there's a region in the middle clouds that's about the same temperature and pressure as the surface of Earth. Now, I mentioned these clouds are made of sulfuric acid, but there is water in the clouds, and there are also various energy sources, chemicals that could be considered nutrients. So it's kind of an out there idea, but depending on how clever life is at adapting to different environments in the universe, which is something that astrobiologists really want to know, we don't know. It's conceivable that some kind of life form could have evolved to live in these clouds. And this is an idea I put out there actually in the late 1990s. And I wrote some papers and had a book about this. And it was kind of, I think tolerated, but not really embraced by my colleagues. But interestingly, recently there have been a flurry of interest in the possibility of a habitat in the clouds of Venus. And there have been workshops and special issues of journals. And for whatever reason, I think maybe because we've learned more and more about the what we call extremophile life that can adapt to extreme environments on Earth, that the idea of looking for life in the clouds of Venus is, I wouldn't say it's become completely respectable, but it's not just me talking about it anymore. There's a whole community of scientists that are studying this possibility now, which I love. I think is great. I'm pleased and entertained by watching how these ideas kind of go into and out of favor over the years. But it's, it's another, I certainly think it's still a long shot, but it's worth looking. It's another reason why the possibility of exploring Venus further is so enticing. One more thing I have to tell you about is a new idea about the evolution of the surface of Venus. This is a paper I co-authored with some colleagues a few years ago. Was Venus the first habitable world of our solar system? I told you the idea earlier that we think Venus had oceans early on, but then the question is, how long could those oceans have lasted? And it turns out when we do more sophisticated climate models of Venus using the same kinds of tools, the GCMs, the general circulation models that we use to model climate change on Earth, it turns out that the oceans of Venus could have lasted much longer than we used to think. And they may, in fact, have lasted for billions of years and evaporated relatively recently, maybe just in the last billion years. This is what our recent model results are pointing towards, although there's a lot that we don't know and a lot that we can make these models much better with the data we're going to get from the upcoming missions. But it's seeming more likely than it did before we did this modeling that Venus could have held onto its oceans for much of its history. And then you have this very enticing picture that maybe the world next door, when all these things were happening on Earth, the origin of life, photosynthesis, more and more sophisticated life, Venus could have kept its oceans while much of this evolution was happening on Earth. And who knows what might have happened with biological evolution on Venus. Especially when you consider that Venus and Earth were probably exchanging material during this time. So if life got started on one of them, it could have spread. So that means that if life got started on Earth, it could have spread to Venus if Venus was an oceanic world like this, or it could have gone the other way and our ancient ancestors could be Venusians. You never know. So anyways, just a kind of cool thought. And another reason, again, why this exploration feels so vital, because it may have been that for much of solar system history, there were two planets right next door to each other, Venus and Earth, that maybe both had oceans and habitable conditions. And it's only more recently that the oceans have gone away on Venus. This is a possibility and something we can nail down with our future exploration. So now I want to tell you about the missions coming up in the decade of Venus. As I mentioned, I'm part of a community that has for years, for decades, been proposing missions. I've lost track of how many mission teams I've been on that have proposed missions to NASA for Venus. And each one of these proposals is a lot of work. It's, a couple of years of work and putting together detailed plans and instruments and specifications and budgets and teams. And, it's like you have to have a credible plan. And I've been part of this project a lot, and I've gotten very used to rejection. And then you sort of, after you get rejected, you look at your colleagues and say, are we ever going to do this again? No, it was too much work. And then NASA comes around with another opportunity and you say, well, let's try again. You dust yourself off. I've done this over and over again. So it was amazing when this proposal that I worked on with a lot of other people, Da Vinci, which stands for Deep Atmosphere Venus Investigations of Noble Gases, Chemistry, and Imaging, our entry probe mission, we got the word about a year and a half ago that NASA had greenlit us. And I swear, when I got that phone call, I was just in stunned disbelief. I was so ready to learn once again that we had been rejected, that I was already like conditioned for disappointment. So when I got the phone call and they said, we won, we've been funded, it sort of like took me a minute. Like, what did you say? And then I think I screamed so loud that I scared my dog. he thought we were under attack, and I had to then reassure him. But that was an unusual feeling. Success. Now I want to tell you more about the Da Vinci mission, but one thing I'm going to do first, or to just sort of set the stage, I have a cool little 3-minute movie that describes Da Vinci. And I think if we can get this to work, Mitch has it queued up and can show this movie now.
Launching in 2029, the Da Vinci mission, named after Leonardo da Vinci, is designed to address fundamental questions about the origin, evolution, and composition of Venus. During 2 gravity-assist flybys, Da Vinci will study the cloud tops in ultraviolet light, tracking cloud patterns as they change with time and analyzing signatures of mysterious chemicals that absorb ultraviolet light. Both flybys will also examine heat emanating from the Venus surface on the planet's night side. We will look for geological clues of this planet's mysterious past to paint a global picture of surface composition and the evolution of the planet's ancient highlands. 7 months after our second flyby, Da Vinci will release its atmospheric descent probe. The spacecraft will watch its probe enter Venus's atmosphere over the course of 2 days. The probe will take about an hour to fall through the atmosphere, taking measurements and snapping images down to the surface. These measurements include profiles of composition, winds, temperature, pressure, and acceleration. Key gases will be measured to help us understand how Venus formed and evolved. Some of these measurements may reveal chemical signatures of ancient water. With our suite of measurements, Da Vinci will provide new insights into Venus's atmosphere's complex composition, structure, and chemistry. As the probe nears the surface, its descent camera will capture breathtaking bird's-eye views of the mysterious terrain known as the Alpha Regio Tessera, possibly revealing evidence in the rocks that water once flowed across the Venusian surface. These up-close images of the surface will provide new insights into geologic processes and will help us to understand what it might be like to stand on the Venus surface. An oxygen-sensing student collaboration experiment will shed light on the role of this gas in the Venus atmosphere. The discoveries that emerge from this diverse dataset will tell us whether Venus was truly habitable, and the story we reveal at Venus will reach even beyond the solar system to analog exoplanets that will be observed with the James Webb Space Telescope. Venus is waiting for us all, and Da Vinci is ready to take us there and ignite a new Venus renaissance.
All right, let's see. I think I need to share my screen again. PowerPoint. There, that's working, right? So yeah, that gave you a little bit of a overall about Da Vinci. And by the way, the voice you heard there was my colleague, Giada Arni. She's a planetary scientist here in the Washington, D.C. area at the NASA Goddard Space Flight Center. And she's the deputy principal investigator of this, of our Da Vinci mission. And so, yeah, we're going to fly by twice, as the video told you, and make movies of the clouds, do some really interesting spectroscopic observations of the clouds. Then we're going to drop our probe into the atmosphere and measure all this stuff during that 1 hour of descent through the atmosphere. And then a really exciting part of this is that the final part of that descent is going to take those descent images of this mountainous region, Alpha Regio. And that's going to just be a brand new thing. And I think that, if it all works, what do I mean? Of course, it's all going to work. It's going to be just spectacular having those descent images of the mountains of Venus. Here's a overview of the instruments we have on the spacecraft. Going from left to right on the bottom here, we have a mass spectrometer and a tunable laser spectrometer. And those are our two real workhorse instruments for understanding the atmosphere, for looking at the ratio of deuterium to hydrogen, that is heavy hydrogen to normal hydrogen, which we think will tell us the story of escape of water on the planet. And looking at what we call the noble gases. That is, if you go to the right side of the periodic table on your classroom wall, and those gases all the way over to the right, krypton, xenon, argon, radon. Those are, we call them the noble gases because they don't react with anything. And their measurements, if we can get detailed measurements of their abundances and their isotopes, that can really tell you a lot about the history of and the origin of the atmosphere. So those are some of the things we really want to do with those instruments. And then the VASI is the Venus Atmospheric Structure Investigation. That will just take really detailed measurements on the way down of the temperature, the pressure, the wind speeds, just really measure conditions all the way down. And then VENDI is our Venus Descent Imager. That's the camera that's going to take those images of the surface and the terrain as we descend to the surface. Oh, and then finally we have VFOX, which is the Venus Oxygen Fugacity Experiment. And what's neat about that is it's going to be a student-built instrument. And it's going to measure what we call the oxygen fugacity, which is basically what is the state of oxygen at the surface of Venus and how reactive is it. So with all that, plus our orbiter, our flyby rather measurements, we're I think we'll really stand to gain a new understanding of the atmosphere of Venus, its history, and the detailed geology of one patch on the surface. But that doesn't tell us the global geology. But that's what's neat, is that there's another Venus mission, of which I'm not on the team, but I'm very good friends with the members of that team, and I've worked on that. I helped work on the plan for that mission in the past, and that's a mission called VERITAS, which stands for Venus Emissivity Radio Science, INSAR Topography and Spectroscopy. Wow, what a ungainly acronym. But VERITAS is going to do some really cool stuff. It's not going to enter into the atmosphere like Da Vinci. It's not going to focus on one place in detail. Instead, VERITAS is going to do global mapping, like Magellan did in the early 1990s, but to a much higher, with much greater detail. It's a, radar technology has become more sophisticated in the intervening years, and we know much more how we want to study Venus. And so this VISAR, Venus Interferometric Synthetic Aperture Radar, is going to get much more detailed topography and much more detailed imaging. The imaging is going to go down to 15 meters. You'll be able to see detail of 15 meters. Magellan was hundreds of meters. So you'll be able to see in much more detail than Magellan. And it's also got an emissivity mapper that can look for active volcanoes and volcanic plumes and look for things about the nature of the rocks on the surface, map that out in ways we haven't been able to do before. So what's really neat is the way these two new missions that are both going to, VERITAS is going to launch in 2028. Da Vinci is going to launch in 2029. The way they're going to complement each other. It's almost like we get one larger mission to study Venus, because the VERITAS orbiter is going to give us really detailed global mapping, which gives us the context for that one spot where we're going to do our entry probe and our descent photography with Da Vinci. So between those two missions, I think we really stand a good chance of answering some of our long-standing questions and solving some of our mysteries about Venus. And bonus, there's a third mission that's recently been approved by the European Space Agency. You know, when it rains, it pours. We went from having no upcoming big Venus missions to now having 3 of them, because the Europeans just approved a mission called Envision, which is going to launch in 2031, so a little bit later. But Envision is also an orbiter, but it's going to have a very sophisticated radar instrument that will map parts of the planet in much greater detail even than VERITAS. So it can map in more detail, but it's not going to make global maps. It's going to make targeted maps of interesting areas. There's a trade-off there, because if you're mapping in really high resolution, then you don't necessarily get enough data to do the whole planet. But again, that's complementary to these other missions. And the other thing that Envision is going to do, which Veritas is not, is a radar sounder. So it can actually, this is a radar instrument that allows you to look at the subsurface. You can actually see structures and materials that are below the surface, and map out layers of material that, and get a more 3D picture of the geology. We've been able to do this with Mars some, but this is going to be our first time that we're able to do it on Venus. So there's really kind of a rich prospect for discovery in the coming decade with these now 3 upcoming Venus missions. And I didn't even mention that possibly the Indian Space Agency is going to send a Venus mission as well. They're talking about it, so yeah, we're up for an interesting decade or two of Venus missions, and it's very gratifying for those of us that have been pushing this for a long time to now see that the world's space agencies are paying attention, and that we're going to go there with new missions and seek new answers. And with that, I'm going to stop my presentation, and I look like I've actually gone kind of long, but I have time, and hopefully if you guys want to stick around, we can do some discussion and Q&A now.
All right, excellent. Yes, everyone, if we understand if you, it's a school night, if you need to go, that's totally fine. But if you can stick around, we do have quite a few questions already. And for anyone who hasn't asked a question, please type it into the chat. Going back early on, you mentioned there were some interesting impurities in the atmosphere of Venus. Tell us more about those.
Yeah, so the clouds seem to be mostly made out of sulfuric acid, but there are clearly some components in the clouds that are not made of sulfuric acid. And by the way, this connects to, I told you, my sort of slightly maybe fringe idea, maybe not, that there could be some kind of possible organisms in the clouds. And one motivation for that, it's connected to the fact that there are clearly some components in the clouds that we don't know what they are that are doing interesting things. There is this stuff in the high atmosphere that is known as the unknown ultraviolet absorber. Not a very good name, but that's because we want to replace that with what it actually is. There's something that's absorbing a huge amount of solar energy high in the clouds. In fact, whatever this stuff is, it's absorbing half the solar radiation that hits the planet Venus, and we don't know what it is. So it's the mysterious ultraviolet absorber. So there's that, and then in the main cloud deck itself, the largest cloud particles seem to have something inside them that's not sulfuric acid. We can tell this by looking at the way they absorb radiation and scatter radiation. There's something about the optical properties of those particles that isn't quite explained by sulfuric acid. We don't know what it is, but there have been some, and it seems like it might not be liquid. There may be something solid in some of these particles. And then there have been a handful of entry probes, the old Soviet and American entry probes, that have done a little bit of measuring of the actual cloud particles. And there's some hints of some exotic materials. The Soviets measured, they said they reported they found iron in the clouds. And there's hints of magnesium and, other strange things that you wouldn't necessarily expect to be in clouds. But again, there's dust blowing up from the surface. Who knows, there could be trace amounts of things. And then you may have recently heard that there was this observation made from radio telescopes on Earth of a chemical called phosphine in the clouds, which is controversial. It's controversial because some people doubt that the measurement was really correct, and people want to repeat it in different ways. But then also, why should there be phosphine on Earth? The only thing that makes phosphine in the atmosphere is life or industrial processes. I mean, things like meth labs actually make phosphine, but I don't think anybody's saying that exists on Venus. But in other words, there's no natural process on Earth that isn't involved with life or humans that makes this weird chemical phosphine, which is a phosphorus with 3 hydrogens. So we're not sure if that's there, but there are a lot of hints of exotic weird chemistry in the clouds that we want to follow up on with our new instrumentation and really try to understand what's going on there.
Yeah, we should send a spacecraft down there.
Exactly.
So people are asking, why no rover on Venus? Is it just too hot?
Yeah. So in the long run, that would be a great thing to do. It's hard to do anything that lasts on the surface for a long time on Venus. It was amazing that the Soviets were able to send these several landers that lasted for about an hour each. And they did it they were just these huge diving bells with like tons of insulating material and tons of, they had this, what they call phase change material, which is stuff that sort of boils off, but it takes a while to boil off and it absorbs a lot of heat. We know now probably other ways to survive on the surface of Venus for a few hours with advanced kinds of electronics and stuff. But to really do a rover, you'd want more time than that. People are coming up with new technologies to solve the problems. And I think it is something we'll do at some point in the future, new landers, new rovers. Eventually, we'd like to do long-lived surface stations. So you could do things like seismology and weather stations. But to do that, you want to last for months. And that's hard to do in those conditions, although people are trying to come up with new kinds of high temperature electronics. There's 2 ways you can go about it. You either cool off your spacecraft, make it into a big, refrigerator and have an environment inside that's cool, or you say we're going to operate at Venus temperature and you design these high temperature electronics. And people are sort of working on both approaches. And I think at some point we will. So it's not that we don't want to do a lander. It's just that with the kind of technology we have and the kind of budgets we have, it's not the realistic next thing to do.
Yeah. So a related question, how long will the Da Vinci probe survive?
Okay. So Da Vinci's prime nominal mission is just to make it down through the atmosphere and to make it to the surface and send all the information back, including those descent pictures. And it's not designed to really survive on the surface. However, it may for a while. We have the ability, if things work out, to keep taking data on the surface. It's just that that's not part of, we're not designing it to do that. Again, it's a question of technology and money, and it will be considered 100% success if it makes it to the surface and sends all the data back, even if it doesn't survive on the surface. But it could. It's very analogous to, you may remember the Huygens probe to Titan, which was our first descent probe on an outer moon, and Huygens was the same thing. It was only designed to make it to the surface and would have been a success if it made it. But Huygens actually did survive on the surface for a while and measured the surface properties and took some great images from the surface. So it was kind of a bonus. So if we get a surface mission at all out of Da Vinci, it'll be considered a bonus, but it's not part of our, we can really do all our science just on the way down, and that's what it's designed to do.
All right, very cool. So given the enormous pressure on Venus, how does that compare to pressures on Earth in the oceans or places like that?
Oh, yeah. So basically, you have to go down deep in Earth's ocean, about 1 kilometer down to get to a depth where you'd have the same pressure as you would have just on the surface of Venus.
So if we made a Venusian rover, it could also explore the bottom of the oceans.
Yeah. In fact, there are a lot of parallels in some of the challenges, of exploring the deep ocean. Obviously, there's some major differences as well, but it is a kind of similar technological challenge in some ways.
All right, cool. Are you writing any more books?
Yeah, I've got a few in the works. And none of them are quite ready for prime time yet. I mean, my most recent book, which you guys may know about, is the one Chasing New Horizons that I did with Alan Stern about the Pluto mission. And I've got a few things in the hopper, but I've been pretty busy with this mission, and I've been writing my monthly columns for Sky and Telescope and doing all kinds of other stuff. But yeah, there will be more books. I appreciate the interest, but it takes a little while to crank one out.
All right, so we have a question about what are the differences between the cloud cover and the landforms on the dark side and the light side of Venus?
Yeah, so the landforms, I mean, Venus rotates, so there is no permanently dark side or light side. So the landforms, are the same, or there's no difference. But the atmosphere is interesting because even though the surface will be in darkness for more than 100 days of Earth days of dark, and then and then light, which you would imagine, you would think that would do something dramatically different to have that long a night or that long a day. But as I mentioned before, there are no temperature differences really, because that thick atmosphere circulates around and redistributes the heat. And the atmosphere, the upper atmosphere, whips around so that every 4 days it goes day, night, day, night, day, night. So it doesn't stay in darkness very long. There are some chemical differences we've measured between the daytime atmosphere and the nighttime atmosphere. And that kind of makes sense because of what we call photochemistry, because the sunlight itself, and particularly the ultraviolet light from the sun, is doing chemistry in the upper atmosphere. It's splitting apart, it'll split apart carbon dioxide molecules. The atmosphere is mostly carbon dioxide into, CO and oxygen atoms. And then they'll recombine on the dark side. So you have some chemicals sort of being split up by sunlight on the night side and then whipping around to the dark side and then recombining. And, so there is some day-night difference in chemistry. But that's the main difference. The atmospheric conditions are pretty much the same. And if you were on the surface of Venus, you'd notice the changing illumination, obviously, between day and night, but you wouldn't notice any temperature difference or anything like that. So we'd be sort of subtle.
So weird.
It is weird. It's a weird place. That's my scientific opinion, is that yes, Venus is weird.
How will the James Webb Telescope help analyze Venus?
It won't really. You can't look that close to the sun with it. It was a question even with Hubble, whether Hubble could look at Venus, because people want to be very cautious, because if you look at any object too close to the sun, you don't want to make a mistake and swing it too far and point Hubble at the sun and completely fry the electronics. That would be wrong. So they got good enough at operating Hubble after many years that they got permission to observe Venus with Hubble, and that was really neat. They got some great images and some great spectra of the clouds and so forth. But it is my understanding that JWST will not be allowed to look at Venus. I'm pretty sure that's true. Maybe that'll, like Hubble, maybe that'll evolve when they get more confident. It's going to do great things in the outer solar system, where you can look safely because you're looking away from the sun. And obviously it's going to revolutionize our understanding of exoplanets, including, Earth-like and Venus-like exoplanets, hopefully. So in that overall sense, it's going to certainly contribute to our understanding of how Venus fits in. And it will, be complementary to some of the investigations we're doing with these spacecraft and so forth. But I don't believe we're going to be able to look at Venus with the Webb.
All right. Well, it's good to be safe with your huge space telescope.
Yes. I mean, everybody's still in disbelief and breathing a sigh of relief that it unfolded correctly and it's out there where it's supposed to be and it launched and it's working. The last thing we want to do is accidentally point it at the sun.
So how much methane has been detected on Venus?
Mm.
And could that also hint at possible life?
Yeah, that's a great question. You wouldn't expect there to be methane or not much of it in an atmosphere like Venus, because it's a reasonably oxidized atmosphere. So all the carbon is going to be in carbon dioxide, not in CH4, methane, especially in it's a hot atmosphere. So chemical reactions are pretty efficient. So you would expect any methane there to chemically decompose pretty rapidly, unless it's being actively supplied. Just like you don't really expect to see methane on Mars, but there's hints of methane on Mars now. And people say, aha, that's interesting, because it means there must be a source, because methane doesn't hang around. So if you saw methane on Venus, it would mean either, there's a volcanic source, or it might make some people think, oh, what about biology? Interestingly, there was a report of methane observed by the Pioneer Venus entry probe that I mentioned in 1978. And that was kind of dismissed. In other words, it seemed so unlikely that several scientists said that's got to be a mistake. There's something wrong with the instrument. You can't have people wrote, it was reported, and then other people wrote papers saying that's got to be wrong, because here's why you wouldn't have methane, because it's so unstable. And so those reports are in the literature, but they were sort of not completely taken seriously. But very recently, some colleagues of mine have done a reanalysis of that, driven by this phosphine measurement that I mentioned. They decided, let's go back and look at the Pioneer Venus mass spectrometer data, see if we can find phosphine. And they looked, and they actually think they found phosphine in that, although it's controversial. And they also think they looked at the methane again. They said, you know what? We think there is methane. So if there is methane, it's really fascinating, because it means, again, either it's a recent volcanic plume, or it could support this idea of biology. Because again, with that one thing that's a clue to biology is when you have disequilibrium in an atmosphere, there are two things. Disequilibrium means that there's a source of chemical energy that something could feed off of. And then life itself often produces disequilibrium. I mean, on Earth, there's methane in the atmosphere because of organisms putting it out there, because of metabolism. And so if you saw methane on Venus, like on Mars, you wouldn't necessarily say, aha, it's life, but you'd say, there's something interesting going on here, and life is at least one hypothesis. So it's up in the air whether there's really methane, and it's definitely something we will be looking at with our new observations.
Very cool. So given the temperatures on Venus, is there any mechanism where the surface rocks melt and flow and denser rock comes up or is exposed? And is there constant flux on the surface?
Yeah, so there's definitely been a lot of geological activity over the history of the planet. We see all those volcanoes that I showed you. And so that means that there's been magma coming up from the interior and being deposited on the surface. The surface, many places, is not ancient. It's maybe 1 billion years, but it's not 4 billion years like you see on Mars. So that means there's been some kind of recycling mechanism. It doesn't seem like it's plate tectonics like on Earth. And there are a lot of different ideas, and honestly, we don't know. This is one of the things that hopefully with the more high resolution imagery from Veritas, we're going to be able to puzzle it out. But there's clearly been some recycling of the surface on Venus, but how that's organized on a global level, it seems like it's not plate tectonics, but there's some idea that maybe there are a larger number of smaller plates that are overturning over time, or maybe there's an episodic activity where Venus gets very volcanically active for a while and then it quiets down. That there are many ideas in play. So it's a great question, and clearly there is a kind of recycling that happens over time, but how that exactly is organized over space and time is something that we're still trying to puzzle out.
Cool. If you were on Venus, could you see any of the nighttime stars on the night side?
Oh, yeah. Unfortunately, the answer is no. If you're on Venus, it seems as though it's pretty much going to be overcast all the time, everywhere. Which is sort of too bad, because it would be interesting to see the stars from Venus. I'll tell you one weird thing about Venus and seeing the sky, if you could see the sky. So I mentioned Venus rotates really slowly. And by the way, it rotates so slowly that if you were on Venus and you walked towards the east, you could keep up with the sun. You could walk fast enough to keep the time of day the same as long as you kept walking. Like on Earth, you have to get into an airplane, to chase the sun and keep, but on Venus, you could do it on foot. But also with that slow rotation, the way it interacts with, it's also Venus is orbiting and passing Earth on the inside lane. It passes Venus 5 times every 8 years. Or Venus passes Earth 5 times every 8 years. And the rate of its orbit is coordinated with the rate of its spin in such a way that every time Venus passes Earth, it's the same side of Venus facing Earth. So it spins around just enough so that every time it passes us, there's a certain place on Venus that if you lived there, that when Earth was overhead, you would always be in the right place. And there's other parts of Venus where if you lived there, when Earth was overhead, you'd never see it. So if you could see the sky, there'd be like the Earth place on Venus where Earth would always be overhead, and other places where it never would be, which is also very strange. It's not the way we're used to thinking about observing other planets. You could see Mars from anywhere on Earth, but that wouldn't be true if you were on Venus. There'd be places where you couldn't see Earth and places where you could. So if we go there, we're going to have to do something about those clouds.
Earlier, you alluded to Venus and Earth sharing material billions of years ago. How does that happen? Okay, well, you know how there are Martian meteorites on Earth in our meteorite collections. In fact, I think there are a couple pieces of Martian meteorites there at the Denver Museum, and there are in a lot of meteorite collections now. And we have those because in the past there were impact events on Mars. When a big asteroid or comet hits the planet, it makes a big enough explosion so that some pieces of the planet get knocked off. Now, it's a little bit harder to do that on Venus and Earth because they're bigger planets. They have higher escape velocity, but nonetheless, you have a big enough impact and there's going to be stuff knocked off into space. And if this is happening enough, and early in the solar system, there were many more impacts. That's why the ancient surfaces of the moon and Mars have so many craters, because there was more stuff flying around the solar system and smashing into planets. So the bigger ones would be knocking bits of the planets off. And some of those bits are going to travel through space, and Venus and Earth are going to, be dropping stuff on each other, just like we have bits of Mars in our meteorite collections, which prove to us that transfer mechanism does happen. Have we found Venusian meteorites? Great question. No, we have no Venusian meteorites, and it's an interesting puzzle why. One theory I've wondered, would we recognize them? Maybe they look a lot like Earth rocks, but you can still tell a meteorite is a meteorite if it's got a fusion crust and everything. And so far we have not found any meteorites that are obviously Venusian, but it may just be that they may be sitting on Earth in Antarctica or wherever, and we just haven't found them yet. All right, cool. So you mentioned that sunlight-driven photochemistry explains Venus's loss of water, and the sun is also responsible for Mars lacking water. How has Earth escaped this fate? Yeah, that's a good one. So if you compare Earth to Mars, the major difference is size, and Mars, being so small, has much lower escape gravity, and so it's much more vulnerable to losing its atmosphere and its water over time. Basically because it just doesn't take nearly as much energy. So, all planets are losing atmosphere all the time, including Earth. There's hydrogen streaming off the top of Earth's atmosphere
every second. It's just not significant enough to really erode our atmosphere over billions of years. But Mars has enough of a loss rate because of its lower gravity that it just couldn't hang on to as water. Now, the Venus-Earth comparison has to do with what I mentioned before, that sort of cartoon I showed where the Venus is closer to the sun, and therefore it just had much more energetic radiation over time that tipped it over that balance where the runaway greenhouse happened. So Earth is in that sweet spot where it's far enough from the sun that it didn't have a runaway greenhouse, and it's large enough so that it had the gravity to hold on to its atmosphere and water over time. And for, basically Mars was too small, Venus was too close to the sun, Earth was lucky.
Just right.
Yes, exactly.
So since the atmosphere is so dense, does that mean the parachute to lower the trobe will be pretty small?
Yeah, that's right. You don't need as big a parachute on Venus. In fact, with some of the past landers on Venus, you didn't want too big a parachute because you don't want to go too slowly, because you don't want to get too hot. So obviously, if you're trying to land on the surface, you want to reduce your velocity, or if you're trying to do a lot of measurements on the way down, you don't want to be going too fast. But a lot of times the problem with Venus is that you're going too slow because the atmosphere is too thick when you get into that lower atmosphere, and you don't want to heat up too much. So in fact, it's useful to have a parachute to slow down when you're higher up. But when you get down lower, you really don't want to increase your drag too much.
All right. Well, this has been great. There is one final very important question. You mentioned in the middle clouds, there's a place where the temperature and pressure is fairly similar to Earth. Would it be smarter to try and colonize Venus in the clouds versus trying to colonize Mars?
It depends, I suppose. If you went to Venus, you'd have to live in a cloud city. Maybe that would be kind of interesting, but it would be very different. I think it's more natural to think of us wanting to go live someplace with a surface where you could actually walk around and do the kinds of things we do on the surface of a planet. So I don't know about, would it make more sense to go to try to live on Venus than on Mars? But I do think that it's something that people will probably try someday. That is doable. It's not like it would take some technology, but it wouldn't take magic. We could find a way to build long-term structures that could float in the clouds, and it would have the advantage over Mars, as the questioner alluded to, that you would be at roughly Earth surface temperature and pressure. So you wouldn't need a pressure suit or anything like that. You would need a breathing apparatus, and you'd probably want something to protect your skin from the sulfuric acid, but you wouldn't need as bulky a spacesuit maybe as you would on Mars. So because you wouldn't need a pressure suit. So there's that. I think they'd both be challenging and interesting places to go ultimately.
All right. Well, this has been wonderful. Thank you so much for joining us. We will be back May 25th. We hope everyone will come back. And do you have any final thoughts, Dr. Grinspoon?
Just that I appreciate everyone hanging around, and I appreciate the questions. And I do miss Denver, and hope to get out there sometime this summer. It's been a long pandemic of no travel. So hello to all my Denver friends and everybody else out there, and have a great evening. Live long and prosper. That's my last thought.
Excellent. Wonderful. And we'll all be eagerly watching the developments with Da Vinci.
Thank you.
Thank you so much, everyone, and have a wonderful evening.
Good night.